Hello everyone. It's been a long time since we met, and I think because of the coronavirus scare, our classes have been delayed a lot. But then I think it was a little essential also not to conduct classes because we need to be responsible and contain the spread of the virus. But nevertheless, we are losing on time for class 12, and I feel it's appropriate for us right now to start with the classes through the online mode. And yes, it does not carry the same effect as a regular classroom session will, but then at least you guys will, start with the syllabus and start practicing at your own end. And we will then resume from the point where we left once the regular classes resume. All right. So, but I don't see any relief in the situation probably in the next week. So we'll have to conduct the online classes only. So let's see, let's hope for the best. And I'm today starting with electrostatics and physics. Right. If you have had the chance to go through your textbooks for class 12, you might have started reading the chapter and understood that charges basically are of two types, positive and negative. And you already understand about electrons and protons. Electrons are negatively charged, protons are positively charged. Now, charge as such, charge is basically the intrinsic property of any matter, right? Just like, for example, if I have an object that has some mass, mass is an intrinsic property. Like the same way, charge also is an intrinsic property of a matter. So in that case, can I say that the article that I'm holding in my hand, is it charged? Well, yes and no. In the sense, since we understand that matter is made up of atoms, and atoms has electrons and protons. And for an electrically neutral object, the number of electrons is always equal to the number of protons. So as such, this object is not charged. Yes, it will become charged when there is some excess of electrons on it or some deficit of electrons, right? Okay, now charges as such cannot exist without the material containing it. In the sense, like, I can't have electrons flying in the air. I need a material. So if this is the material and this material has excess of electrons, yes, this will be negatively charged. If this material, from this material, if I extract certain amount of electrons, yes, this will be positively charged. But I need the material for any charge to exist. Now, there are some ways by which we can make an object charged. In a sense, like I have an object here, and this is not charged right now. So I have a concept which is called as charging by friction, which is called as frictional electricity. Now what exactly is that? Frictional electricity means if I have a glass rod, let's say, and I have a cloth, maybe a woolen cloth or a silk cloth, and I start rubbing it, right? Now that motion, that friction generated between the object and the cloth will cause some of the electrons to transfer from one object to the other. It generates energy so that electrons can shift their position. They can shift from one object to the other and thereby making the body charged. Now, I'm not generating electrons out of nowhere, right? I'm just transferring electrons. So as such, if I add the negative charge attained by this and the positive charge acquired by the cloth, just a random example, the total charge would still add up to be zero, right? So if one object loses electrons, the other gains electrons, right? Okay, so this is what charging by friction is. It is called as frictional electricity. There is another term you might have come across which is called as electrostatic cling. I think a lot of us have experienced using a cellophane paper, or like you have a cling wrap available in the kitchens, or even then, even so, a very thin sheet of plastic, when rubbed against your body, will always stick to it, right? That's because of the charge is present on it, right? And I think most of us have done this experiment of taking small bits and pieces of paper, using a scale, rubbing it on our head, and then seeing that the small bits of paper gets attracted to that scale. Right. That is also because of something called as cling. By rubbing, I have charged the scale, which now is attracting small bits and pieces of paper. So that's also one thing that we should keep in mind, that this effect is also because of the electrons and protons, and mainly electrons, because protons are not defined, because of electrons. Talking about frictional electricity, I am taking two substances. For example, if I take a glass rod and wool, or if I take glass rod and silk cloth, or if I take silk and some metal, and if I rub them together, which one would acquire a positive charge and which one would acquire a negative charge? Okay, so there is a series, we call it a triboelectric series. Triboelectric series is a series of materials which are arranged in an order in such a way that the substance occurring earlier in that series, when rubbed with a material occurring later in the series, the former will acquire a positive charge and the latter will acquire a negative charge. Probably you can see that series on the board right next to me. Right? Based on the properties of a material, all the materials can be divided into three basic categories. First, a material can be a conductor, it can be an insulator or a co-conductor, and third, it can be a semiconductor. Now, conductors are usually substances which have free availability of electrons, so that electrons can travel on the surface and hence conduct electricity. Semiconductors are substances which conduct electricity, but not to that extent as a conductor does, and not as poorly as an insulator does, right? And insulators, as you all understand, that insulators are substances which do not conduct under normal circumstances. Yes, I can have an insulator conduct, but under special circumstances. What will that condition be? We'll probably talk about it later. Coming back to charging an object, we already discussed about frictional electricity, and I mentioned about charging by induction. Now, what exactly induction is? Induction is basically the phenomena of polarization of charges in a body when when another charged body is present near it. Polarization of charge in the sense, like if I have a sphere, a metallic sphere, which is electrically neutral otherwise, because it has the same number of electrons as the number of protons present. And what I'm doing is I'm bringing a charged object near it. Suppose I have a positively charged metal plate like this, and I bring it in close vicinity to this uncharged metallic sphere. Now what's going to happen is, since it's a metal, it's a conductor, and therefore it has a lot of free electron availability. Now because of that electron availability, the electrons on the surface will get polarized, the charges will get polarized, the negative charges will skew and come on one side of the metal sphere, and the positive charges will realign and come on the opposite side, right? Now, at this particular instant, if I provide a way for these positive charges to neutralize themselves, in the sense, if I connect the sphere with the ground, in that case, what happens is electrons, because ground is said to be a source of infinite charge. So electrons from the ground will flow to the sphere, will neutralize the positive charges, and the net charge that remains on the sphere will be negative. I will then remove this particular charged object, and the net charge that remains on the sphere in that case will be negative. So basically what I have done is I have induced charge, induction. I have made the charge polarized that's present on the surface, and then once I have all the positive charges on one side, I neutralize these charges by connecting it to the ground. Right? There could have been a different scenario. In the sense, instead of bringing a positively charged object in a sphere, I could have brought a negatively charged sphere, object. Like in this case, if had this been negatively charged, then the polarization would have taken place in this manner. All the positive charges would have accumulated on one side of the sphere, and the negative charges would have accumulated on the opposite side. In which case now, if I connect this sphere one second, if I connect this sphere now to the ground, I will provide a path for these electrons to flow to the ground, and as a result of which there is only the positive charge remains, positive charge that remains on the sphere. I can take away this key, and hence the result that I will be having is I will be having a positively charged sphere in front of me. There is another method by which I can charge the two spheres. Let's see. If instead of taking one sphere, I take two spheres like this, right? Both spheres are electrically neutral, hence do not have any excess charge. It has the same number of electrons as the number of protons it has. And now in this case, if I bring a charged object near it, like we did in the previous case, suppose this is negatively charged. Because of polarization of charges, all the positive charges on the two spheres combined will accumulate on one side, and the negative charges will accumulate on the other side. Now, the charges from both spheres can interact because the spheres, I have just joined them together like this, right? And since these are metallic spheres, these are conductors, therefore charges from one sphere can travel to the other one, right? Okay, so what happens after this, that once the polarization of charges has taken place, I can slightly separate the two spheres, thereby preventing the polarized charges from flowing back. So the net positive charge remains on this particular sphere, and the net negative charge remains on this particular sphere. I can remove the charged object now, and now I have two spheres. This simple method actually, I now have two spheres which are charged, which initially they were uncharged, but now I managed to induce charges on them by this method. It's called as charging by induction. Next, we talk about some properties of charges. Now, charges are additive, right? I'm going to write down. Charges are additive in nature. In the sense, if I have a charge of plus 5 coulombs and minus 2 coulomb, I'll add them and get 3 coulombs of charge, right? Charges are quantized. When I say quantized, I mean that every charge is an integral multiple of the charge that is present on an electron. An electron or proton has the same numerical value of the charge, which is 1.6 into 10 raised to the power minus 19 coulombs. A value we should remember by heart by now. 1.6 into 10 raised to the power negative 19 coulombs. This is very, very small charge, and yes, we have been able to find smaller charges than this, which is called quarks. but we are not using it mathematically. So yes, for all practical purposes, we understand that the smallest charge possible is always the charge that's present on an electron, which is 1.6 10 to the power minus 19 coulombs. If it's a proton, it's positive 1.6. If it's an electron, it's negative 1.6. Right? N is an integer. So every charge is always in multiples of the electronic. If a conductor is charged, the charges will always remain on the outer surface, right? Unless, of course, it's a solid object, like if I have a solid cylinder or a solid sphere, then the charges will be inside the body as well. But otherwise, in case of a hollow object, charges will always be on the surface. Very much because of the same reason that charges will be on a substance. If it's hollow, there is no material, and if there is no material, there cannot be any charge on it. The distribution of charge may be uniform or non-uniform. If it's uniform, it can have a linear charge distribution, it can have a surface charge distribution, and it can have a volume charge distribution. Two charges will always exert forces on each other. Like charges repel and unlike charges attract each other, which brings us to a very important theorem or very important law, which is called as the Coulomb's law. And we'll discuss about the Coulomb's law in the next video.